So which ones have we covered so far? We've covered p-values for mean with known or unknown sigma. We've covered difference of means.
Yep. Variances.
With known and unknown sigmas. If they're unknown,
They have to be the same.
either they have to be the same, so if they're unknown, assume that they're the same, and then you do something, or assume that the number of,
And it's large.
yeah, if these are large, then you just pretend that they're known, because they're a good substitute, theoretically, for the true variance. Okay? And we know what to do. This is a z statistic, this is a t statistic, known is a z statistic, unknown but equal is a t statistic, unknown unequal but NA is large is a z statistic, right? And you don't have to have this memorized. You just think about it every time. What information do I have? How do I get this? How do I cook this up into something whose distribution I know? Right? Any questions? Then we did we do already sigma squared variance?
Yeah.
Okay, so then we did variance. Variance by itself. How do you do variance?
Chi-squared.
Chi-squared, right? Variance will be distributed by chi-squared. And we have not yet done variability. Okay, so now let's do ratio of variances. So let's get p-values for ratios of variances. So let me give you an example. So let's compare the variability. So we have steel brands A and B. Steel brands A and B. And let's compare the variability of the two. So what do I mean by that? So let's sample, we're going to sample how many? 13 of the first one. We observed a standard deviation, a sample variance rather, of 19.2. For the second one, and B, we sampled 16 steel brands, and we observed a, kind of not even trying anymore with the example, I'm just saying steel, but I'm not telling you what about the steel, what are we measuring, whatever. There's an NA and a SA squared, there's an NB and an SB squared. SB squared is 3.5. So the question is, right, this is 19, this is 3. Could it be that they're the same and it's just, what are the odds that we saw this much variability just as a fluke? So the null hypothesis will be that the variances are the same, and the alternative hypothesis, let's do a two-sided alternative hypothesis, that they are different. All right, let's test the null hypothesis that they are indeed the same. How in the world would we do this? Right? Does the letter F kind of float into your prefrontal cortex or something, right? Float into your brain. So how do we make an F distribution? Remember, an F distribution is chi-squared with n degrees of freedom divided by n, divided by a chi-squared with m degrees of freedom divided by m. So in our case, what will be our chi-squared?
NA minus 1 SA squared over 6A squared.
Right, so other than Ernest, I hope everyone still remembers this. That is our chi-squared. NA minus 1 sample variance divided by true variance, divided by the number of degrees of freedom, divided by NA minus 1, because that's the number of degrees of freedom. And in the denominator, the same thing with B's. NB minus 1, SB squared over sigma B squared, divided by NB minus 1. The NA minus 1 cancel on top and bottom. The NB minus 1 cancel on top and bottom. Now we're going to get this statistic under, as usual, assume the null hypothesis. Assume the null hypothesis. If the null hypothesis is true, how unlikely is this F value? right? If the null hypothesis is true, then what's sigma squared over A over sigma squared B? 1. That's the whole point of this null hypothesis. What if I wanted to test that the variability of one is twice that of the other? Or by the looks of it, maybe 5 times that of the other? Right? That would be my null hypothesis, that sigma A squared is 5 times sigma B squared. This ratio would be a fifth, or 5, wherever it is. Okay?
Squared over is 5.
Sorry?
Yeah, the sigma B squared over sigma A squared. Yeah.
Exactly. So this ratio, the sigmas, which we don't know, we're assuming the null hypothesis. That means the F distribution literally is SA squared over SB squared. Okay? This number is SA squared is 19.2, SB squared is 3.5. And some of you asked if I could actually do the calculation so that you, in front of you, so you could see how they're done in Wolfram Alpha. So let's do that. Let's see what we need to compute. So this is going to be some number, and this number will be a value of F. What does an F distribution look like? It's positive because it's chi-squared, ratio of chi-squared. So this is what an F looks like. We're going to get some number. Let's call this 20 in that 4. So we're going to get a number like 5 or something. The true number is 5.49. Okay, that you don't need my calculator for. So this is 5.49. That's the value of F. Now that will be only alpha over 2. And then there's another alpha over 2 down here because we're testing a two-sided, bless you, two-sided null hypothesis, alternative hypothesis. It's not symmetrical, but whatever alpha over 2 is over here, it's going to be the same alpha over 2 on the other side. So we don't need to even figure out what that number is. Does everybody follow that? Can you see? So, so what is this going to be? What is this value? Half of the p-value. So the p-value will be twice times something. So how do I get the area under this curve?
Tail, so 1 minus C.
So it's 1 minus the cumulative distribution function, because it's the tail. So 1 minus the cumulative distribution function of an F distribution with how many degrees of freedom?
NA minus 1.
NA minus 1 and B minus 1, so 12 comma 15. 12 comma 15. At what value? At 5.49. Right? So that's the number we need. Let's pull it up just to show you how to do this. I guess I'll do it once and then you'll see. So let's go to Wolfram Alpha. No, not Wolf Spider. Wolfram Alpha. Here's Wolfram Alpha. Can you guys see this? Is this big enough to be visible? There we go. Zooming in. Okay, so what do I want? I want 2 times 1 minus the CDF of an F distribution, caps lock, F distribution with 12, let's say n equals 12. I hope this will work. N equals 12 and m equals, what did I say, 15 degrees of freedom. That's my F distribution, comma, at 5.49. Please work. Yes. F distribution, n equals 12, m equals 15. And that's the PDF and the CDF. And the percentile's good, but so it's possible that this extra, and sometimes this extra bit confuses it.
You want a time symbol?
I don't think I want a time symbol. I want a CDF, usually CDF F distribution. Yeah. It's finding the F distribution, but it's not giving me the CDF of it.
It's sliding.
It is?
Yeah, it's only for 12. When you hover over it, it's only for 12 months.
Can I edit this? No. Come on, I did this at home and it worked. I don't know what extra buttons I pressed. F distribution, well now it's
You can backspace, it'll go back to the.
yeah, okay, good point.
If you just type like, maybe like at 5.49, like after the.
Yeah, how about at x equals, whoops. At x equals 5.49. Sometimes it specifically wants, so the first thing I did is 12 comma 15, and then it thought 15 was the CDF, so I knew not to do that.
I guess you just
Maybe the parentheses are at CDF of F distribution with this many degrees of freedom at x equals 5.49.
Professor, can you just ask the p-value of the distribution?
I could just ask with p-value. Fine. Well, let me type it in literally how you would do it in Mathematica code. That should work. CDF of F distribution. How do I do an F distribution? F distribution, Mathematica. Just called F ratio distribution? Yes, F ratio distribution NM. Copy. Paste. F ratio distribution NM, comma, 5.49. This should not have any ambiguity. It should not have to do anything except output what it would do if I was using Mathematica. And it got it. Good. So now I want 2 times 1 minus this. And that should be a direct 0.0027. And is that the number I got at home? It is. Okay, so the point is it's not entirely trivial to figure out how to code these things, but a little bit of Google and you'll figure out. So the input in the end was CDF of the distribution, comma, the place where you want that CDF. 1 minus that CDF gets me the tail instead of the bulk up to that value. And twice because that's the p-value of the alternative hypothesis, 0.0027. That's what I'm going to keep. Let's go back to the docam. So I'm going to keep 0.0027. Bless you. Okay? So that's how you get these numbers. That's what I mean by you no longer have to look up tables. Do not look up tables, just Google it. Ernest.
Why do you multiply by 2 again?
Okay, our alternative hypothesis is not a one-sided hypothesis, it's a two-sided hypothesis.
Yeah.
So the critical region, there's an implied critical region. The implied critical region is of the shape sigma A over sigma B differs from 1 by something. So if they differ from 1 by something, then there's a region here and a region here that we're going to throw away. And we'll make both of those regions half of the level of significance. And the question is, where is the point at which this particular instance that we observed would have gotten thrown out? What's the least alpha for which this observation would have us reject the null hypothesis? That's the definition of the p-value.
Okay. So you throw away the lower tail because it's like pretty high.
Well, I'm not throwing away a lower tail. My observation happened to be this way and not the other way.
Okay.
The other way would have given me 1 over 5. 1 over 5 would be down here. And the density would be, well, it would be 1215 at 1/5, but it's the same distribution. The F distribution has this symmetry, right? When you switch the 15 and 12 and you reciprocate, because it's the same thing, right? If I take 1 over this, then I'm computing the same thing just with switching the degrees of freedom. Does that make sense?
Yeah.
So had I chosen to do it the other way, I would have gotten this number 1/5 and computed this distribution. Or this way is this upper bound. Doesn't matter which way you want this inequality to go, we're going to catch values that are too large and values that are too small. Now, if we were doing a confidence interval, we would choose, do I want 3/4 here and 1/4 there, or half and half or something? So in this kind of idealized scenario, we're just going to assume that it's half-half. If I have a two-sided tail, whatever tail I actually got, which is a one-sided tail, I just double. Does that make sense?
Yeah. It's just like, why would you do a two-sided? Like, why not just have all the alpha like on the right? Because it's like-
So you set up the experiment before you know what the outcome will be.
But if you did like one side, why would you multiply the p-value by 2?
It's a two-sided.
Yeah, but if you did like one side.
If I did a one-sided, then I wouldn't multiply by 2. If I did a one-sided, if I just want to know, is sigma A bigger than sigma B? But I should ask that question before I run the experiment, not after.
Because like when you see the ratios, it's like already you know it's gonna be like pretty high. So like.
Right. So that's running the experiment and then trying to fit the data to the experiment.
Yeah.
Which is dangerous because how what your underlying assumptions are, if that's affected by what you've seen, you could get into a feedback loop. Right? The better way to do things is you first set your parameters. That's why people decide on their level of significance that's why people were happy with that protocol. You set your level of significance so we know what the rules of the game are, then you play the game. You don't play the game and then say, actually, I'm allowed to score with my hands in soccer. It's like, wait, we had rules. So you make the rules first, and then you play the game. So maybe I wrote it in the opposite order of, maybe that's what's giving you the impression that your alternative hypothesis should be sigma squared is greater than sigma b squared.
Yeah.
Because that's what we observed, right? We observed this massive, that SA is much bigger than SB. So why would we even bother with the other side? But the point is we didn't know which way it was going to come out until we ran the experiment. So we had our null and alternative hypothesis first, then we ran the experiment, we got that that SA was the bigger one, but it could just as well have come out the other way, we don't know. Unless that's what we're trying to test. So it depends on what you're trying to test. If you're trying to test sigma A is bigger than sigma B as the alternative, then you don't have to double the p-value.
So what if you're doing the same test, but then your f value is actually really, really small?
So if we were testing, let's say we're testing sigma B is greater than sigma A.
Just like two-sided. Like, what if everything's the same except your data is like your f value comes out to like 0.2 or something? Like, would you still do 1 minus CDF?
0.2? So
Like, if
0.2.
your f statistic was 0.2 instead of 5.4.
Great. So the whole point is our critical region is here, centered about 1. So if we wind up in 0.2, then we're in the other version of this. And so now you would just run the CDF and not 1 minus the CDF.
Okay. So depending on what your f value is,
Yes,
you wouldn't
depending
do
on which
1 minus
side
CDF.
of the mean you wind up on, you try to figure out what's the critical region that would have resulted in that tail. So it does not make sense to say the critical region would have been, I don't know what it would have been if this entire thing is the tail. The tail can't contain the mean. Does that make sense?
So what
Yes?
you wrote up there about the critical region, shouldn't it be the absolute value of sigma A over sigma B minus 1?
Yes,
Right in the
thank you, minus 1.
Because
Yeah, or you can take logs.
Yeah.
That's another way of doing it. Because log of something, log of 1 is 0. Yeah, so thank you, yes. So I want to catch this ratio being away from 1. I mean, there's a whole variety of why multiplicatively and not additively, right? That's what log would do. Do I want just 1 on either side? Well, I don't want 1 on either side, because if I go 5 in this direction or 5 in this direction, I'm in negative values. And there's no point in catching negative values. So I do want to do this multiplicatively. If this is out to 5, this should be down to 1/5. So
Either way though, like the -1 in the critical region, can't you just absorb that into the K?
No, because it changes where it's centered.
Yeah.
You're just trying to find the deviation of the ratio.
Yeah. So log is a good way of doing it. Okay, but the point, the main point I'm trying to make is, if you're trying to understand ratios, you're going to use an F. The null hypothesis lets you get rid of the unknown sigmas, because you're assuming the null hypothesis, so it tells you something about the ratio. And then you get an F value. You think about what kind of test you're trying to run to figure out if you need to double the p-value or not, and whether you need 1 minus the cumulative density, because your observation was in this tail, or just the cumulative distribution itself, because you're taking that tail. And then that's the p-value. Any questions? Yeah, Justin.
So if you did on one side, the alpha would be completely different.
Well, the p-value would be half of this p-value.
Yeah. Okay.
So I wouldn't double it. That would be the only difference if I was doing a one-sided
So the
test.
significant region would be exactly half of what you do two-sided.
By definition, the volume,
Yeah.
just because we're choosing alpha so that this area is alpha over 2, and we're choosing this point so that this area is also alpha over 2. So yeah, it's not an accident. It's just by definition that's what we're choosing to make our critical region. Taylor.
Okay, that's not really good. So, like we're doing all this stuff because we're using sigma squared A is not equal to sigma squared B. But if we were going to do that like one-sided, would we still be including the -1, or couldn't we just?
Yeah. So if we were doing one-sided, so let's write this down. If one-sided alternative hypothesis was something like sigma A squared is bigger, bless you, than sigma B squared, then our critical region would be, well, how much bigger? Right? Where do we want to reject? We want to reject 1 sigma A squared over sigma bless you B squared is bigger than something.
Okay, cool.
So that was just shorthand. So really what we want, I mean, maybe a better way to put this so that I'm not using absolute values and we really see what's going on, is sigma A over sigma B is at least K, or sigma A over sigma B is at most 1 over K.
1 minus. -1.
So now I really want the ratio, because this is the outcome of taking the log. Right? I want to catch when I'm bigger than 5 or when I'm less than 1/5. So that's what I mean by this kind of critical region was an additive critical region around 1 of the ratio, whereas this is a more appropriate multiplicative region. And if you took log of sigma A over sigma B and caught that in absolute value in some interval, that would have this effect. Should I say that more precisely? Let me say that more precisely. So observe. This is some very basic stuff, but let's spell it out. Observe. Here's another type of critical region. Here's a critical region. Log of sigma A or sigma A squared, doesn't matter, over sigma B in absolute value is less than, let's call it K. Observe what happens to this kind of critical region. So this critical region, oh sorry, the critical region is where we would reject the null hypothesis. So we want outliers to this, right? If the ratio is very close to 1, then the log is very close to 0. Log of 1 is 0. You can put the squares or not. I mean, it's the same thing. But, right? Because something squared, the log of that is a 2 here, which just changes the constant by a 2. Yeah. There's a 2 both on top and bottom, and so if there's a square in parentheses, that square comes out and can replace K. So this critical region is equivalent to what? Well, first of all, it's equivalent to log of the ratio being bigger than K, or log of the ratio being less than negative K, right? That's how you resolve inequality being bigger, an absolute value being bigger than something. To be bigger than it, you either have to literally be bigger than it, or you have to be less than negative that value. K is a positive number. And so if I exponentiate this, this is equivalent to, I'm going to exponentiate both sides. Sigma A over sigma B is bigger than e to the k, and this is equivalent to sigma A over sigma B is less than e to the minus k, which of course is 1 over e to the k. So that's what I mean by the critical region. If you're just testing one-sided, then you may as well test that the ratio is bigger than something. That's the ratio being bigger than something. With squares, where you can take, square root of k. And the other side is what I was saying back up here. The other side is what I was saying up here. The ratio is either bigger than k or the ratio is less than 1 over k. So that's the same thing as what you would get if you took logs for your critical region. Okay, does that make sense? All right. That was a ratio. Let's talk about proportions. Any questions on ratios of variances? That was p-values for ratios of variances. Let's do p-values for proportions. P-values for proportions. So let me give you an example. So 4 out of 20 patients suffered a serious side effect of some drug. Suffered. Okay? Our underlying assumption, we're trying to determine whether they suffered randomly or whether there was some, the treatment didn't work on them or something. And maybe it doesn't work on half the people, but we observed not half, but not 10 people, but 4 people experiencing something. Okay? So what's the underlying assumption? That's supposed to be a colon. When we're talking about patients or coin flips or candidates, Bernoulli, right? So these are Bernoulli trials, independent Bernoulli trials. Human beings are IID, identically distributed with the same parameter, Bernoulli trials, with parameter theta. Right? So theta is the probability that you suffer. So let's test the null hypothesis that theta is equal to 1/2 against the alternative hypothesis that theta is, let's say, not 1/2. And let's find a p-value for this particular experimental outcome. So what would you do? Yeah, we only have 20 patients. So you should be a little careful about assuming the central limit theorem. But you actually don't have to assume the central limit theorem at all for any of these computations. Because what you're going to do, so in order to analyze the p-value, so what is our random variable? Our random variable is nx bar, right? This, the total sum, this is just the sum of the xi's. The xi's are IID Bernoulli. That's a random variable. And what's the distribution of it? Binomial, right? So this is distributed like a binomial with parameter
20.
N equals 20.
right, n equals 20, and theta equals, we don't know theta, but we're assuming the null hypothesis. Whenever you're computing a p-value, it's assuming the null hypothesis, how unlikely is this outcome. So we get to assume the p-value, but that means we know everything about the distribution. So what is the probability that we got such a small outcome? So the probability that our variable took on such a small outcome
Summation, right?
exactly, it's just a summation. It's just a sum as k goes from 0 to 4 of the probability that you had this many observations of a Bernoulli random variable, but we know exactly how to write that down. So this is 20 choose, I guess I'm calling it k. You want to call it I? Let's call it I. 20 choose I, theta to the I, 1 minus theta to the 20 minus I. Right? That's the probability of an outcome, this much of a tail of the outcome over the Bernoulli. You stick this in Mathematica, let me not spend time doing it. The outcome is 0.0059. This I think you can literally stick in 20 choose I, and this, by the way, since this only happens when it's a half, this is just 0.5 to the 20. Ernest.
You need to multiply by 2 since you're doing two-sided.
Exactly. That's the probability. So again, a Bernoulli is a discrete random variable, but it's a discrete random variable. Let's say I have some mean somewhere. So it's a discrete random variable. I can still plot its distribution, its density function like this. So because it's a two-sided alternative hypothesis, what I really want is the probability of getting a result that differs from the mean by this much. So this is really equivalent to nx bar minus the mean, which, assuming theta is a half, would be 10. So this is nx bar minus 10 is less than, well, -6. But what we really want to catch, that's just one side. We want to catch both. What we really want is the probability that nx bar minus 10 is at least 6. One piece of this equation is this equation, that's down here, 4 and below. The other piece is this equation, 16 and above. But by symmetry, they actually have the same probability. So we don't have to compute the sum as I goes from 16 to 20 of this.
So that's symmetry because of the half.
It's symmetry because of a half.
Okay.
Symmetry because of a half. Yep. So so the true p-value will be twice this probability. So p-value of this outcome is twice 0.0, help me out, 0.128, 0.0118. Right. Okay? Now again, this is 0.01, a little bit more than 0.01. So if you had your significance, level of significance at 95%, this is significant. If you had it at 99%, it's not significant. Emily.
I'm sorry. Why did you rewrite it again as the probability of nx is less than or equal to 4 as nx minus 10 is less than or equal to -6?
So the true probability that we're trying to catch, our implied critical region in this assumption, right? To do a statistical test, we need a null hypothesis, an alternative hypothesis, and a critical region. The implied critical region is of this shape. And then the question is, what's the least probability, or what's the likelihood that you saw something in this region? And we observed 4, which differs from 10 by 6. And so what's the probability that whatever outcome you got differs from 10 by at least 6? That's the two-sided tail that we're testing. And so one side of it is nx is greater than 16, and the other side is nx is less than -10 is less than -6.
Right. Okay. Because the proportion is 1/2.
Because the assumption that we're testing against is 1/2. Okay. Good. So that's there's no approximations here. We didn't say pretend that this is that central limit theorem has kicked in. Pretend it's Gaussian. You can just literally compute these things. There's no reason. Even if you had 100 variables, 100 observations, there's still no good reason the computer can sum 100 numbers really fast. There's no. You'll get almost the same answer. So let's see an example of that. I think I have an example of that. Yeah. Before we move on, any questions on this example? Let's do one more. One more example. So one more example. Slide this up. Example. So I have an oil company. Oil company says that there are at most 20% of all drivers that have not used its oil. Have not used its oil. Okay? In other words, it's saying a lot of people have used its oil. At least 80% of the population has used its oil. We're going to test, so the null hypothesis, so whether or not people have used their oil as a Bernoulli random variable with some parameter theta, identical. We're going to test their claim by saying, well, what is the probability that they have not used its oil? So theta is, so the probability that that one person has not used the oil is theta. So H naught is that theta is at least 20. 0.2. That's what we're trying to
That's what we're trying to reject.
reject. Okay? We're trying to reject, if we want to prove this claim, we want to reject the opposite claim. Okay? So we want to reject this null hypothesis. And the question is, can we reject this null hypothesis? The alternative hypothesis is what we're trying to show. That fewer than 20% of people have not used its oil. Can you see what's there? Is that what that frown is?
Yes.
You can't see. Let's see if this will help.
No, it's more like I don't know what that little thing is.
Oh, that little thing. Let me just write it all again. I mean, it almost doesn't matter what the words are. The null hypothesis is that more than 20%, that theta is more than 0.2. The alternative hypothesis is that theta is less than 0.2.
Wouldn't the greater than or equal to sign be on the second one? Because it said most 0.2? Is what they said?
Yeah, if you want to be careful about equal signs, maybe I'm not being. Says less than, yeah. So no, it says less than 20%, so H1 is less, strictly less.
Oh, okay, so this, yeah.
So that is actually consistent. But those end cases will never matter. So what do they do to try to prove this? They tested 200 drivers, of which 22 had not used the oil. Had not used their oil. So they say, aha, if only 20% of the drivers had not used their oil, out of 200 drivers, we would see 40. And we're seeing much less than that, 22. So doesn't that prove our point? And you, the statistician, says, wait a second, is this enough of a sample size? Yes. Just.
I'm slightly confused by the company because you say the null hypothesis is sigma is less than 20%, and then go from there. Wouldn't that just be easier for them to prove?
So remember, only when you can reject a test, you're rejecting the null hypothesis. So you're saying the null hypothesis is not true.
What happens if, like, even if you set it to be less than 0.2 and you just fail to reject it every time?
Well, if you fail to reject, then there's not enough information.
Okay.
We're not accepting the null hypothesis when we fail to reject. Taylor.
I was kind of confused about this because in the book it said that we couldn't accept something because we weren't looking at like the power of the test. So.
Right, and here we're also not exactly looking at the only way that H1 comes in is whether it's a one-sided or two-sided.
But, sorry to cut you off. But if we did the power in this example, like as an add-on, then we could accept it, or?
Well, then you could argue, so what you would argue, if you run the test and you determine what your p-value is, and you set that to be your alpha, from that value of alpha, now you have a set critical region. It's a little bit cheating because you're setting your critical region after you've seen the observation. But never mind, let's say that is our critical region. Right? You're supposed to set your critical region first. Then you see whether or not your outcome landed there. What a p-value is doing is it's saying, given the outcome, what critical region would have resulted in rejection? Okay? So So, but let's ignore that for a second. So say we chose the critical region once we did the experiment. And then, given that critical region, you could compute the power, what's the probability of a type 2 error, and try to argue that, well, if we're rejecting in favor of the alternative hypothesis, then we're this certain that we haven't incorrectly rejected the null hypothesis for the alternative.
Okay.
Did I answer your question?
Yes.
So the p-value, you're absolutely right. The p-value is missing a lot of information that you would get from complete, alpha and beta analysis. The problem with the complete alpha and beta analysis, you have to choose alpha first. And a p-value, and that's an arbitrary thing, whereas a p-value is, this is what happened, what value of alpha are we actually seeing? Did that answer your question, Justin? Mostly. Can you ask your question again, and let's see if I can do a better job?
You basically answered my question previously when you answered it, so it's
Okay.
Yeah.
Okay. So the point is we want to reject the null hypothesis, so let's set up the null hypothesis to be the opposite of what we are trying to prove. Right? Okay, so we tested 200 drivers, 22 of them had not used their oil. So what are we going to do?
I think that's a lot of drivers.
Okay, so one thing we could do, let's do two things. One is let's repeat the previous computation. So what did we do? Binomial distribution, right? Nx bar is binomial. So what is the probability that Nx bar is, let's get half of the probability, is less than or equal to 22, assuming that 0.2. 0.2 is the hardest thing to test in this range. That's the boundary of H0. So we're going to test it. We're going to assume H0 at the most extreme level. Right? It's the most likely outcome given the data. If the true theta is a half and we saw 22 instead of 100, that's even less likely. Does that make sense? So the most likely outcome given the data is the extreme value, 0.2, allowed by the null hypothesis. So that's the hardest thing to disprove. It's much easier to disprove theta equals 0, theta equals a half, because then we should be seeing 100 drivers instead of 22. So the hardest thing to disprove is the boundary value, 0.2. So that's the probability we're going to compute. What is it? It's a sum as I goes from 0 to 22. The binomial coefficient, 200 choose I, 0.2 to the I, 0.8 to the 200 minus I, and you can compute this, and you get 0.0005. Okay? So I doubled that to get my p-value. No, because it's a one-sided inequality. I'm only interested in a one-sided inequality, so that is the true p-value. So that really suggests rejection. 200 is a lot of people to test. Now let's see what would happen if we tested instead of a binomial probability, if we tested a Gaussian. So alternatively, since n is 200 is large-ish, large, and again historically people would call 30 large, we can do something else. We can approximate the binomial by, so nx bar has mean and theta is 0.2, and variance right, n theta 1 minus theta. So this thing is a standard normal. This is a z. Bless you. So now I can put in nx bar is, the x bar is 22 over 200 times 200, that's 22. Nx bar is the sum of the xi's, so it's just how many did we see. how many drivers, whatever C means. How many drivers had not used their oil? 22 drivers had not used their oil. 22 minus how many drivers should have used their oil if the true value was 0.2? 40. 200 times 0.2 is 40. Divided by square root, well now it's just numbers, 200 times 0.2 times 0.8. That comes out to negative 3.18 on your calculator. And now I'm checking, given that I have like more than 3 standard deviations away from the mean on this Gaussian normal, what is the cumulative density function of a standard normal? In other words, what is phi of negative 3.18? That you can plug into Wolfram Alpha, and you get 0.0007. Okay? So in absolute terms, these numbers are quite close, in the sense that in either case you would definitely reject the null hypothesis as being less than 1%. On the other hand, in relative terms, the difference between 5 and 7 is like 40%. Okay? So there's really no reason. It's so easy these days. In the days of tables, no one took their binomial table out to 200. In the days of, you Google this on Wolfram Alpha, there's no reason to approximate a binomial by something, by the central limit. If we know exactly what the distribution is, just compute the distribution numerically. Okay? Any questions on that? All right, we got one more to cover, and this is like the most important thing. This is the key to all of the scientific method. It's the difference in proportions. Differences among proportions. Why is this the scientific method? What's the scientific method? You run an experiment. You also run a control. Okay, the scientific method, you run a control and you run an experiment. Maybe you run 6 experiments at the same time, and you want to know if there's significance above the control. Okay, so let's talk about differences among proportions. Let me start a new page for this. So here's what we're going to see. We're going to see some observed self-frequencies. So here are observed. These are called self-frequencies. So we have sample 1, sample 2, maybe sample 3. And we see how many number of failures, what do I want to do, number of successes. And there's more general versions of this, but let's start at the beginning. Number of successes, number of failures. So this is the frequency of sample 1, and 1 will be successes. And this is the frequency of sample 1, where 2 is the failure. So we have a matrix. A K, if there are K samples, let's say there are K samples, sample K. This will be FK1, FK2. So we have a K by 2 matrix of values, matrix of frequency values. Let me give you an explicit example, a very concrete example, and then we'll figure out what to do with it. So we're going to figure out, we have candidates A and B, and we're seeing how they poll in LA and New Orleans and New York. Okay, here's candidate A. Here's candidate B. And the question is, who do they prefer? Success is they prefer candidate A. Failure is they prefer candidate B. You're working for candidate A. So that's your success versus failure. NOLA. New Orleans, Louisiana? Okay. All right. Let me just give you some numbers, since these are the numbers I pre-computed. 260, 240. This is 197 and 203. All right. So the first thing you should notice, the first thing you should do is look at the totals, which is summing your table this way. 168 plus 232. It's 400. So they really prefer, I mean, to sum, the halfway point is 200. There's quite a big difference here between people preferring candidate A to candidate B. How about in New Orleans? We managed to sample not 400 but 500 people total, right? 240 plus 260. And there's some small amount of relative favor for candidate A. In New York, they like candidate B, but only a very little bit better. In the sum of those, we again got 400 samples in New York. Okay? So then there's a total number. Total sample, which we'll call N1, N2, down to NK. Of course, this is the failure. This is frequency 1 plus frequency 2. Okay, the total sample size in each sample. And our null hypothesis, let's test the null hypothesis. So this was candidates, but maybe one of these is a control. So if you have a control versus the other things that you've seen, and these are proportions, right? Bernoulli trials, everything is assumed to be Bernoulli. And the null hypothesis will be that the theta for sample 1 is the same as the theta for sample 2 is the same for sample k. And let's call it some value of theta 0. Now maybe you know theta 0. I don't know why you would know theta 0. In practice, you don't really know theta 0. In other words, does everyone understand what we're saying? We're saying LA is our control, or forget about candidates. It's not really a good, there's no good control for candidates. But if we were running some drug and we had placebo, right? Sample 1 is placebo. So think sample 1 is placebo. So I don't know why LA is placebo, but let's go. Okay, so there's the proportion that have some effect. We want to know that our drug has had some effect. Placebo is no effect. And let's say we tried drug 1, 2, and 3 against placebo. Did any of them do better? So the null hypothesis is they all did exactly the same. They didn't change anything. Yes?
What is theta naught?
So theta naught is just if we think that we know what the proportion should be, then we say our null hypothesis is that they're all a half, or 0.2. In practice, we don't know theta naught.
So that's a fixed value.
That's a fixed value, yeah. So if theta naught is known for some reason, use it. If not, which is most of the time, well, then you need an estimate for theta 0.
So we just take a weighted average.
Right. So we want this, so this is called the pooled. This is the pooled estimate. What should our pooled estimate be? Well, we've seen all of these observations. We've seen all of these successes and failures, and we know what the totals are. So why not just take all the successes we've seen, divided by all of the trials? Okay? So this is F11 plus F121 plus F31 out to Fk1. These are the successes, divided by N1 plus N2 plus Nk, divided by the total number of trials. Okay, so this is the pooled estimate along all of the trials that we've seen. Okay, does that make sense? So that will be our theta. And then, what are we going to do with all of these variables? Well, we can certainly treat them all as, so NA X bar A minus NA theta A, but we're assuming in the null hypothesis that they're all the same, so let's call it theta hat, divided by the square root of NA. I guess I'm calling them A. I should be calling them ones, because we're gonna have more than just 1 and 2. N1 x1 x bar 1 times theta hat 1 minus theta hat. This is a Gaussian, Z1. Then we have another Gaussian, Z2. N1, N2, x2 bar minus N2 theta hat over square root of N2 theta hat 1 minus theta hat. Is another Gaussian, and so on, up to Zk. We have all of these Gaussians, and we're trying to see what is the likelihood that indeed these are all Gaussians. So this one comes out to -3, and this one comes out to 2, and this one comes out to 4, and so on. Maybe we should just add them all together, right? If we add a bunch of Gaussians, we know what that distribution is. Right? If we sum the Gaussians, if we take the sum of the Gaussians, we get something that's distributed like normal with, each one was normal with variance 1, now we have normal with variance k. Is that a good test for whether or not these values are all around 0?
No.
Why not?
Because they can cancel out.
They can cancel out. Just summing them is a bad idea because a -3 here and a +3 here will make it look like that value was likely. This is a bad idea. The signs can cancel. What's that?
I'm not listening.
Oh.
Sorry.
So what's the big idea?
So we square.
Square them.
Your absolute values are horrible.
Because absolute values are not so good and their distributions are nasty, but if we square them, so good idea, take z1 squared plus z2 squared plus zk squared. Why is that a good idea? What's this distribution? Each one is a chi-squared with 1 degree of freedom. We've added k of them. We get a chi-squared with k degrees of freedom if theta 0 is known.
Right.
And if we use the pooled estimate, then we've already snuck in a bit of this information in there, so it ends up costing a degree of freedom. For the same reasons as before. That is why the chi-squared test is so central in science. Because what are you going to do when you have a bunch of Gaussians? You don't want to add them up. They could wash each other out, right? A large negative deviation could wash out a large positive deviation. So the standard thing to do is you square them, add them up. That's a nice distribution. That's exactly what a chi-squared is. So that will be our chi-squared test for a set of proportions. Okay, so that's what we're going to do. So let's do it in this example. How do I show you everything at once? Here's our example. Here is our example. So our chi-squared with how many degrees of freedom? 2. 1 less than k. K is 3 samples. Will be. So I'm going to square a bunch of stuff. What's the first thing I'm going to square?
232.
Right. It's n. It'll be convenient to see. How do I show you this at the same time? Well, you know how to make a z variable out of this. It's nx bar. Nx bar here is 232 minus n1 theta hat. N1. Oh, we have to compute theta hat first. Sorry. Theta hat is, I add up all of the successes, 232 plus 260 plus 197, and I divide by the total number of people that we surveyed, which is 800 plus 500, 1300. That comes out to 0.53. Okay? So everybody sees how I got the pooled estimate for theta? All the successes divided by the total number of people we asked. That's a little bit more than half, which is consistent with the data that we saw, except you can't see the data. There it is. Okay, 232 minus, how many people did we see? 400 times 0.53 divided by the square root of 400 times 0.53 times 1 minus theta, 0.47. Squared. Then the next thing. In New Orleans, we had 260 minus 500 times the same 0.53 squared, divided by the square of the square root, so you can actually simplify things a little bit. 0.53, 0.47. Does everybody see that? There's a square root in the denominator that gets squared, so just don't bother, and only square the numerator. And one more term, which I'll slide up in a second. In New York, there is 197 minus 400 times 0.53 squared on top, divided by what's on the bottom is 400 times theta times 1 minus theta. Does everybody see that? So all of these variances from the expected values added up together give me a chi-squared value of 6.47. I do not know where that is on my chi-squared distribution, how far out it is, this 6.47. My alternative hypothesis is just that they're different. And so I just want to, you see, this alternative hypothesis, I mean, I didn't even write down the alternative hypothesis. It's that they're all different, but the difference, it's not a two-sided thing. The chi-squared only gets large. You're taking something that's supposed to have value 0, and then you're squaring it and adding them all up. So all we care about is the large values of this. Small values of this do not contribute to, if they're all 0, then this sum will be small, and then that's consistent with, then we can't reject the null hypothesis. So in this case, it's only a one-sided tail. Even though the alternative hypothesis looks like two-sided, it's just the negative of the null hypothesis. But the way that it's formulated is just a one-sided tail, because we want to see large deviations from the truth, from the supposed truth. Okay, so now I want it, so the p-value is 1 minus the cumulative density function of a chi-squared with 2 degrees of freedom at this value of 6.47. 1 minus because I want the tail and not the bulk. The cumulative distribution would be this whole thing. You compute that, and it comes out to 0.039. So can you reject or not? It depends. It depends on your level of significance. Okay? So here was the original candidate totals. We cannot say that people like candidate A differently than candidate B among the 3 cities with a great deal of certainty. Ernest.
So for this one, there's no such thing as like a two-sided test.
There's no two-sided test for this because if the values are all small,
Then it's like the HO is accepted.
right. So the only way we reject it is if one of these is an outlier, and the way they become outliers is the value of z is either large or small, the square of which will always be large. So if we're summing all of them, that catches were any of them large. And as you can imagine, New York is the real outlier. But that's a further step in the analysis. The first step is, was there something significant? Or do they all behave roughly the same? The drug didn't do anything. What we saw at the placebo is the same thing as what we saw with drug 1, is the same thing as we saw with drug 3. Okay. All right, you're going to have a homework problem. I'm out of time. You're going to have a homework problem. The general setup of the chi-squared, let me just say, chi-squared with k minus 1 degrees of freedom will be a sum. What did we do? I'm just summarizing what we did here. The frequencies I1 minus n I times theta hat squared divided by square root of ni theta hat 1 minus theta hat squared. So don't square root. So that was the sum, and you're going to have a homework problem to convert this into another way of doing things. Do I want to say this now? I guess I have 1 minute, so let me say it. So the expected cell values, as opposed to the true cell values, the F1, Fi1, and Fi2 are the observed success and failure for F. The expected cell values, Ei1, will be Ni, the total number, times theta hat. Right? What's the expected value? I mean, this is the expected value. And the expected failure will be Ni times 1 minus theta hat. So you have a homework problem that's basically just algebra. Turn this into another summation, which is sometimes useful, sometimes not. Fij minus Eij squared over Eij. And this is a sum over I going from 1 to however many samples there were, and j going from 1 to 2. 1 to 2 being successes and failures. So there's a little homework problem about, it's basically algebra, if you get stuck on it. Oh, it's not due till Friday, so okay, I'm okay. We can talk about it in office hours. But it's very simple algebra that you guys are all capable of.
There's no square on the bottom.
There is no square on the bottom because there's a square root squared. So it turns out that this is what happens. Okay, have a good weekend, and see you on Tuesday.